This is a solution to the fourth question on the 2014 physics paper. It's the Joules law experiment. If you'd like to skip to any part of this, just click on it. What's this question about? It's Joules law, which is that formula there. Power equals current squared times resistance. And they wanted to make a graph from this, so they fiddled around with it a bit, and they found that the change in temperature and the current squared, if you graph them, they're actually proportional. Okay, what does that actually mean in real life for normal people? It means that the more electric current you jam into your kettle, the faster it makes tea. That's pretty much what Joules law means in real life. So you're asked to draw a label diagram of the apparatus using the experiment. There it is. The calorimeter is this whole thing here. The heating coil is that wire that gets really, really hot, like in a light bulb or in the bottom of your kettle. A joule meter just measures the amount of energy in joules. You've got to have your variable resistor so you can turn up and down the current. You can measure the current using this ammeter here. Okay. So you're first asked to draw a pseudo graph to verify Joules' law. You've got to make a new table here, of course. You've got to square all those currents. So let's take an example. You take your 1.5 there, you put it in your calculator, 1.5 squared equals, and you get 2.25. So write out your whole table again like that for I squared. You then take your temperatures and you subtract 20 degrees from each of those to find the overall change in temperature, and use that in your new table. And once you've done that, you can draw your graph. Don't forget, you've got to have a few things like the axis labels. That's in current is in amps and temperature degrees or Kelvin there. You want your 6 points all plotted. You do lose a point if you screw up. So just try and get it right. You have a straight line with a good fit, and that'll do. But how does this graph actually verify Joules' law? That's the classic answer, isn't it? You just say a straight line through the origin shows that the square of the current is proportional to the rise in the temperature. Okay, so basically a straight line means that this at the bottom is proportional to this at the side. And then you have to use your graph to estimate the highest temperature of the water if a current of 1.6 amps flows through for 4 minutes. Okay, don't mind the 4 minutes, that's just for the experiment. So you can kind of ignore the 4 here. You take the 1.6 amps, and you can't just have current because we've got current squared going on here in our graph. So we've got to square that 1.6. Then we can use it in our graph once it's been transformed into 2.56. We take that in our graph, we go up to the line, we ricochet like a bullet straight across, and we hit somewhere on the axis around 5.3 degrees. Okay, and then if the temperature change is 5.3 degrees, then we can just say that the initial temperature, the starting temperature at 20 plus that 5.3 will bring us up to the highest temperature of 25.3 degrees. And that'll get you the 3 marks, plus the 3 marks you got from just writing down 2.56. You then got to say why a fixed mass of water is used. Well, kind of makes sense. If you've got a near empty kettle, it should take about 10 seconds to boil. A full kettle will take longer, won't it? So definitely the mass does affect the time for the temperature to change. That's what we're kind of explaining here. We just say that in kind of a more science language, temperature rise is proportional. That means as one goes up, the other goes up, to the current squared, but also proportional to mass. So a change in mass would be an additional variable and has to be controlled, kept the same.